All right, so started. These mics are too powerful. Uh, so this is a special talk. I think this is the first talk ever with audience participation and with a photosensitivity notice, and I'm really excited to see to learn about color blindness today and technology that Dr. Nathaniel Borenstein is working on to help people with color blindness. So Nathaniel is a research faculty at UMSI and CEO of Colorfy. He's been an internet researcher, activist, standards maker, and entrepreneur since 1980 and is best known as co-creator of the MIME standard. Is that how you pronounce it?
Mhm.
Yeah. For which he is often oversimplistically called the father of the email attachment. He's founded 4 companies, been through 2 IPOs, and served as an IBM Distinguished Engineer and Chief Scientist at Mimecast, has 29 patents, and his first book, Digital Integrity, is coming out in 2025, so pretty soon. He remains guardedly optimistic that the internet will do more harm than good in the long run, and we all need optimism these days. So let's give him a warm welcome.
Thank you. Thank you. For the record, I'm optimistic that it will do more good than harm. Just to be clear about that. And it's my 3rd book. But other than that, thank you. So thank you for coming. What I'm going to talk about today, we'll have a little bit of flashing, not too much, but we're trying to be very careful for people who are sensitive to flashing. First thing I want to do is change the title of the talk. When I announced this talk, I had been trying for 9 years to come up with a good general term for this kind of algorithm. And I finally came up with one since then. And for some reason, there we go. So it's actually chronochromic visual algorithms. By this, I mean algorithms that use time and color together to convey more information to the brain. All right. So chronochromic visual algorithms, basically they are animated modifications of images, whether they're still or moving, that encode non-visible information as colors. Now, non-visible information for you is different than what it is for me, because red is basically non-visible for me. But the techniques that I'm describing are going to allow you to see ultraviolet and infrared and things like that with similar results. So these are modifications that happen differentially over time. They're not always there. They're typically rhythmic. It turns out that the rhythm of this helps you to understand what's going on. And as the research goes on, we're going to have I think, very sophisticated rhythms involved in this. It works best binocularly, although I'm showing it today just as single images. But the brain is very good at combining the images from the 2 eyes. And so you can also use these techniques to cause different colors to go to the different eyes. And you can apply these techniques to all or part of an image, which becomes more relevant for some of the more sophisticated uses. This is new enough that there are lots of potential thesis topics in here, and I'm going to flag them as I go along in the hope that somebody's looking for a thesis topic. This is being commercialized as Colorfy, a company we founded. I don't need to say anything about myself since Sabina just did. You can Google my name if you care. I'm the only Nathaniel Borenstein in the world. I co-founded this company with an old friend, Tom Neuendorfer, who's a programmer for the last 50 years. Christian Poe has come in to run the company. I'm hoping to back away from the company and spend more time at SI, actually, because I don't want to do companies anymore. And about a dozen volunteers, several of whom are here. Shun Ukiyama, sitting back there, wrote most of the interface that we're releasing today, actually our first 2 interfaces. So you'll see some of that come by. I see Adit in the back. Adit is a student at Huron High School who's been helping us. Are any of my other students here? I don't think so. Oh, there you are, Bhumika. Hi, I didn't see you there. Bhumika has just graduated last year with her master's and has been helping us out on design stuff, most of which hasn't made it into this first product, but it doesn't mean it's not good work. It means we were scrambling really hard for this first release. And there's several others too who aren't here. This is being done on a mixed commercial volunteer model. I wanted to do this to help the colorblind. And if that's all it did, I would just be giving it away. It also has potential for multispectral vision and things that the military is very interested in. And I will take their money if they want to do that. But we're trying to make sure that all the things we do for the colorblind will be available to everyone in the world for free. Okay, so color blindness or color vision deficiency, which is the proper term, seems like it is a minor handicap. There are plenty of people with worse handicaps, but it's a real one. It affects 1 in 12 men, 1 in 200 women. And the problems that it involves, first of all, you can't fly an airplane. You cannot get a pilot's license. You can't get a commercial trucker's license. In Romania, you can't even drive a car, which I think is unreasonable, but I'm glad I don't live there for that reason. So there's vocational issues like that. There's also daily life issues for all of us, color-coded graphs and objects, red line documents, things like that. Every time I check out at a store, the cashier will say, press the green button. And unless they're also marked with O's and X's, I have to ask which button is green. Not a deadly handicap, but a real one. More troublesome are spoiled or undercooked food. My wife is here. She can tell you she's probably had to 1,000 times say, yes, that's safe to eat, because you get paranoid if you're colorblind. I absolutely can't tell ripe bananas from unripe ones. And I'm going to have some special things to say about muffins later in the talk. It also causes problems with choosing clothes or applying makeup. Almost every colorblind person I've ever known has some story of being embarrassed by people making fun of their color choices. Ed here is nodding. I've never, fortunately, felt much desire to apply makeup, but I understand for the few colorblind people who do, it's a real problem. But most of all, I've always wondered about the beauty that I'm missing. Whenever people are rapturous over a sunset, I think, well, that's pretty, but I can tell I'm not seeing anywhere near all of it, and now I know. Okay. But the truth is, you're all handicapped. You're all kind of handicapped, because what you call the visual spectrum is about 1/3% of the electromagnetic spectrum. I see 1/4%. So it's not really that different. And the things that I'm doing to try to get up to your 1/3% are going to help you too. So you're almost as spectrum blind as me. There has been some technology for the colorblind. I've tried all of it. The most basic one is oversaturation. Back in the days of analog TVs, nobody liked for me to turn their colors because I always made them apparently so garish people wanted to run from the room. Binocularity helps a lot. The first real technology that I used back in the 1970s was the X-chrome contact lens. With this, you put a deep red lens in one eye and an ordinary one in the other, and things that are red sort of jump out. I thought that was the coolest thing ever when I did it. Okay, this is much better. But I was one of those people who never could adjust to contact lenses, so I had to give them up. And then in the 1990s, I actually had special glasses made, you can see here, in which I tried to get that same effect, making my left eye filter through red. It was not quite as good as the contacts, but I still wore them because sunsets were prettier and things like that. In the 2000s, some glasses you might have heard of called the Enchroma glasses came out. These sort of guide the light through sort of waveguides to separate colors better, which is related to a technique called Daltonization that can be done online. The Enchroma lenses are really, really helpful to a small subset of the colorblind, which unfortunately does not include me. And there's been a few other tools. You can get color identifiers, and you can get color vision deficiency simulators, which are a lot more useful to you than to me. Because, as far as I can tell, they're programs that don't do anything. They change a picture to itself. I started working on this stuff back in 2015 with my friend Tom. You can see here one of our early test subjects. That's Google Cardboard using a phone to see more colors. We've been working on this for nearly a decade. Our third patent is pending. It started as a hobby, became a stealth project. That ends today. This is all available as a free web app as of today, and I'll tell you how to get it at the end. Well, not all available. There's a free player, I should say. So this all came out of a sort of information theoretic approach to color vision. If you see RGB, which is one way of modeling what you see, I see RGB. I see this tiny little bit of R. And you get 24 bits of information to make your colors on your screen. I'd probably be fine with about 18 bits. That would do me. So they can make cheaper monitors for me. But if you think about it, there is a fire hose of information pouring at the eyeballs at every moment. You have about 125 million rods and cones. If you represent a color as 3 bytes at 30 frames a second, you're talking over 100 gigabits per second of data coming at your eyeballs. It's actually probably way more than that. So just a ton of information pouring into your eyes. But the brain has to really quickly turn that into, hi, Mom. recognizing something and making sense of it. So there's obviously a ton of compression, if nothing else, going on there. And a lot of this comes out of gaming the compression techniques. So one of the most common techniques for compression of video in MPEG, and I suspect strongly also for your brain, is assuming things don't change. So if you look at an MPEG data stream, it doesn't keep saying for each pixel, still yellow, still yellow, still yellow. It tells you when it changes. And that's how video gets compressed to a reasonable size. It's probably what's going on in your brain. So the brain is very sensitive to changes. And this is all about changes in color over time. So chronochromic visual algorithms multiplex information over time and spectra. And they can incorporate a number of techniques, including variations of hue and saturation, scene segmentation, high saturation, which, as I said, helps the colorblind often, binocular differentiation, persistence of vision, which you've probably all heard of, which is what makes motion pictures look smooth, is also a big part of it, and also fundamentally rhythm. If the color changes are in a rhythm, it becomes easier to understand what you're seeing. The first reaction to some of this is sometimes confusion. Very old people have trouble making sense of what I'm about to show you. But before I show it, everything I'm going to show you is real except for this slide. This is a simulation that should work for all of you. This is matched pictures of a pair of flowers in visible light and ultraviolet light. And I am going to, I have an animated GIF that shuffles them together to illustrate like the world's most basic chronochromic algorithm. So if you watch this when it gets fast, that starts out slow, but when it gets fast, you can basically see, come on, you can see both at once, right? And you're getting the information from the visual image and the ultraviolet image at the same time. This animated GIF slows down and shows and speeds up. So that's sort of the basic phenomenon in its embryonic form. It turns out there's infinite ways to do this. Our current prototype, I recently figured out, has about a sextillion decillion settings, which is an inconceivably large number, right? And there's going to be lots more. And the best algorithm to use turns out to depend on three things: the nature of the user's vision. Like Ed and I have protanopia, which is red weakness, but there's several other kinds of color deficiency. The nature of the image. If an image is mostly red, you're going to use a different algorithm than if it's mostly blue, or the best algorithm will be. And your purpose in viewing it. If you're a dermatologist looking for problems on the skin, you're going to have a very different set of things you're looking for than if you're a makeup artist applying makeup. And so the best algorithm for a given purpose will also change. Because there are so many algorithms possible, and because everybody's different, we anticipate people will want favorite algorithms that follow them from device to device. So from the beginning, we're linking this to authentication. We're using Google authentication for now. The idea is you'll be able to save your favorites and go from your TV to your phone to your computer and have your favorite algorithms there. Eventually, image analysis and AI analysis will be able to choose the best algorithm. And you can imagine like going from the blue room into the green room and having your headset automatically change algorithms. And you might also consciously change it for particular tasks or purposes. All right, so all of those things are potential thesis topics for those of you looking for thesis topics. Finding the best algorithm for particular purposes, for particular types of problems, and for particular, and choosing among such algorithms based on a scene. Okay, so it's time for a demo. The demo is going to have three main parts. First, I'm going to just show you what these CVAs, these chronochromic visual algorithms look like. Then I'm going to show you a little bit about how to use them with the tools we're releasing. And then I'm going to show you how you design new CVAs, which is the really experimental part for those of you interested in research. You ready there, Ian? You got that going? Okay. So those of you who don't know, this is Ed here. He's volunteered to be one of our, he's going to prove to you or not how colorblind people respond to this. So Ed, you've never seen any of this, right? Okay. All right, so let's start with, Ed has already told me he doesn't see anything in either of these pictures to speak of. Is there anybody in here who has trouble seeing what's in these pictures? Don't be afraid. You have a little trouble? So you might be on the low end of color vision, like you might not be colorblind, but you might be on the low end. If you want to sit in the front, you can. All right, so anyway, I'm going to turn on our very simplest algorithm. This is just a Q rotation, where red goes to blue, goes to green, that sort of thing. All right, here we go. Ed, can you see it? What does it say? Yeah, I did not change the image. All I changed was an algorithm running on the image. Okay. Did this get any easier? Where was the? Yeah, did this get any easier for you? Yeah. Okay, cool. You might want to take a color blindness test sometime, see where you come out. All right. I'm going to do a few. I'm going to do 2 more sort of color blindness test type demos. Oops, sorry. So a lot of you may have trouble with some of these because these are of differing difficulties. So just take a moment and sort of say to yourself, oh, these are all easy, or the J is hard, or whatever. All right. Ed, do you see any of these? How about now?
I can see all of them except D.
What's wrong with the Z? I'll have to investigate the Z. This is not my drawing. I got it off the net. What's that? I'm sorry?
B's not there before or after.
I see it.
Okay. You see the Z?
Like it's one frame.
Yeah.
Okay. So like I said, these are different difficulties. So what you're seeing now, if you can see it with this, but not without it, you're actually getting a taste of a slight bit of color blindness, right? Okay. So this next one, it's not technically a color blindness test, but I think of it as one. Oh no, I'm sorry. Where did it go? Just a second. Okay, these have got scrambled in order. Okay, so this is a test I call Find the Redheads. All right, and each of you just think to yourself, how many redheads are there on these screens? Okay, come up with a number, because you won't all come up with the same number. All right, and now Ed, is your number 0? Okay, number 6. Yeah, I think that's the reddest. Okay, we're going through a saturation rotation only on reds here. And as most of you can probably see now, there are 3 redheads. The one you're most likely to have missed is number 4. That's what's called a strawberry blonde, I am told. And that is new to me recently. So this is what it looks like naturally. And what's that? Oh, what a waste. So I'm curious, how many people saw all 3? How many saw 2? Okay. This next one gets us into the area of the practical. So this here is, second. We still have a little problem with our image scaling. So there's a hidden message in here, which most of you can probably see. Ed, can you see the hidden message? Now, who else cannot see the hidden message? Okay, so most of you can see the message. Here it is, Ed. Oh, wait, it's frozen. Oh, this happens now and then. This is experimental software. Sorry. It's not being shared anymore. Oh. No. It's actually the wrong. There we go. All right. Easier to see, Ed? Yeah. Okay. Yeah, this is still software that will occasionally crash on you. So this kind of graph is the bane of my existence. For me, at least, the lower 3 lines are the same color and the top 2 lines are the same color. How are you doing, Ed? Okay. How many people have trouble with some of them? Anybody? Okay, you'll still see why this is easier for us. So this algorithm is the same Q rotation combined with moving bars that either show it or not alternately. And for graphs, that creates a particularly nice effect. As you can see, it becomes really easy to trace the lines. All right. Moving on, I promised you muffins. So these are 2 muffins. And I like to say a colorblind person's life is full of really minor annoyances. Dozens of times in my life, I have bitten into a muffin expecting chocolate chips, and gotten cranberries. Okay. And, you know, not the worst thing in the world. And I like cranberries too, but when you're expecting chocolate, it's just wrong, you know. But if I could look at it like this, Ed, you can tell which of the cranberries now?
Yes.
Yeah. Okay, so again, different algorithms for different purposes. This is one that's intended to draw your attention to red. So,
So Nathaniel, question. So I mean, like you talked about your algorithm. So could you maybe describe the physics behind it, or like what?
I'm going to get there. Okay, that's the end part of the demo. So, but I do want to get to my favorite part of the demo, which is beauty. So here, for example, is a picture of an Indian butterfly dancer. And I find this both beautiful and colorful without any help. Ed, what do you think? Pretty picture? Okay. Well, that's not going to change. You see anything more? So for me, at least, there's all sorts of things, especially in the flowers around her neck, but in the shades on the butterfly and so on, that are the same to me until I set this going. I'll show you one or two other examples, and then I'll get into the meat of it more. When I look at the night sky, it's basically monochrome because color vision is related to brightness, and the sky is dark. So to me, this is pretty close to a monochrome picture. Ed, do you see a lot of colors here?
I see like lighter areas.
You see it now. Okay. All right. So yeah, for me, this is frankly staggering to look at. It's so much fun. And I could show you pretty pictures all day, but instead I'll tell you a little more about the software. Actually, why don't I just show you one or two more for Ed particularly. This is a work of art by a friend of ours, actually. You see all the colors? Do you think you see all the colors?
See what I think is color.
Okay. How about now?
See more.
More colors? Okay. So yeah, there's all sorts of differences in here that aren't necessarily clear. All right, so that's probably enough of the demos for now. Let me, of those demos, let me go to show you what we're releasing first. This is the Colorfly web app, Colorfly player. And it has very simple controls. You can turn the animation on or off. You can choose from a set of preset algorithms. There are 17 algorithms we've loaded it up with. 5 of them are designed to be useful for any kind of color blindness. 4 of them were, tuned to my kind of color blindness, protanopia. The other 8 are guesses for the other 2. I haven't done much research into what works best for the other types. There's lots of research opportunities here to figure out what will help colorblind people the most. So you can switch from one algorithm to another. You can switch from images to another. This is what a sunset looks like. And you can use the camera. So you can see that I'm wearing a very colorful sweater. Actually, let me switch to this algorithm. Sorry. There. So anyway, I think it's cool. Next, I'd like to show you, so this is the product we're releasing today. The thing that's coming down, sorry. When I look down, I get over amplified. The thing that we're releasing not too long afterwards is the Colorblind tuner, which is similar. It's also interfaced by Shun Ukiyama in the back there. It has the same functionality, but a lot more. You can go in and tune up the algorithms in various ways. So for example, right now this is just doing a high saturation hue rotation, but you can say, well, only do it in the red parts. Well, how red? And slide this along, and now only the reddest parts are doing a hue rotation. So you have various things you can tune, and this is something that you'll be able to use to like start with these preset algorithms and modify them in various ways and upload your own pictures and capture other windows. Actually, I'll show you that. What the heck? Just a second. Where did it go? All right, so I'm going to use this. So now I've captured another window that happens to be showing this picture of a Quetzal, and I'm going to use it as an occasion to show you that it works fine with video too. It's all fast enough for that. So this will probably be also released for free to the public pretty soon. Then I'll begin to answer your questions, Paramavir, by going into our Colorblind builder, which is where we design these new web applications. And actually, the way I'll do that is I'll just bring it up into the here. So the demo I was giving you all along there was actually, this was what I was steering it from. The Colorblind builder can use two different windows. Let me find the window it's showing. There. Okay, so I was going to here and I was changing things and they were showing up there. So the way this works is we have a number of controls that configure the algorithm. And by the way, there are many, many more possible. There's lots of room for research here into newer and cooler ways to do this. But the kind of things we have obviously brightness, contrast, and saturation, which are pretty basic, although we can use them in combination with these other things. For a hue rotation, we have a range of start to end. Right now, it's doing 180 degrees of the circle, which is usually enough. But if you want to do the whole hue rotation circle, did it just stop working? It's not doing anything, is it? It hasn't been doing. It's really fun doing research into this stuff when you can't see the colors, by the way. I think I have to reload, sorry. Sorry, this is real and experimental software. Okay. There we go. Okay, so for example, right now it's doing a 360-degree rotation. You can configure that to only go through 180, just 360 or vice versa, which is generally more aesthetically pleasing when you're using it for aesthetics. You can also narrow it down to smaller regions to go through that, which then slow it down, spread it out to be useful for examining certain things. You can also, you have this thing called red focus. Let me switch to a better picture, just a second. Yeah, this one's pretty. All right, so the base picture looks like this. All right, this is it with a hue rotation. But now if you only want to apply the hue rotation to the reddest areas, you can take this red focus and slide it up. And now you can see that the things that are changing are just the reddest parts. And because of the rotation, you see differences as it goes through the cycle. You can, of course, change the speed of the cycle. So I can make it go faster. Not at all clear that there's a one speed that's right for any one person, even all the time. Turns out to be complicated. There's also a pause, which you can use if you want to be frequently comparing what you're seeing. So right now it's cycling for a little while, and then it's stop. The cycles between pauses set very high. So this way you can just sort of watch it and compare it to the base. And that lets you set up a rhythm, which is sort of a bass rhythm that you can couple colors to music, for example. But it's also, in my experience at least, having a rhythm to the colors makes it easier to figure out what you're seeing. You know, it's like red, green, blue, red, green, blue, or something like that. So you're really bringing other senses into your accounting for the color. Another thing you can do, like on a particular picture, you might find that the red focus, like here, everything's moving. You get to here, and only some things are moving. Oh, just a second, it's off screen. And that right now, the red focus is 0.24. So it starts to get interesting here. Now less and less and less things are, now I'm down to the sort of the reddest things, and that's 0.4. So now I can say, I'd like it to cycle between, say, 0.24 and 0.4 every 500 milliseconds, every half a second. And now you'll notice it's rather different. Now it's still doing that hue rotation, but the area that it's doing in is varying over time. And that's showing you more differences. That's giving you an idea of red, red, or reddest to some extent. So Paramveer, does this start to answer what you were asking?
So I was asking more the sense that, so we know, that why are people colorblind? Because the rods and cones are not working properly in the retina or so on. So we're just wondering how all these controls maybe get around that weakness. Like how are people able to see, like from a physics of the eye standpoint?
So I think physics is the wrong way to look at it. I think it's information, okay? Because my eyes are broken, from a normative standpoint, right? And this doesn't fix them. But what it does is it allows the information I'm not capturing about reds to get to my brain otherwise, and the brain is remarkably flexible. So color scientists tend to say color is in the mind, not the eyes, and I'm sure there's some truth to that. I'm not a color scientist, although I'm starting to get some enthusiasm from people who are. Yes.
Is there a machine that looks at the eye and gives you a result? And then related to that is, can your software also potentially help with actually detecting what kind of color blindness can be?
To accurately characterize what kind of colorblindness a user has, there's a couple of tests. The one I see as the gold standard is called the Farnsworth-Munsell test, which is easy to remember. That's just Farnsworth-Munsell. And that involves taking a bunch of tiles with hues and trying to arrange them in the right order. By the way, without any assistance, I get like the same score as randomization when I do that. With Colorfy, I get near perfect scores. Okay, so it really does allow me to do that. People ask, does it let you really see color? Well, in the physical sense, no. In the sense of being able to do tasks I couldn't do before or appreciate more beauty that I couldn't see before, then yes. So I think this comes down to, do I see color? It's a question of how you define the word see. I more often say I perceive colors, perceive more colors. Okay, so that's the kind of, there's other little features, but you get the idea. We have a number of algorithms and a number of ways of tuning them, including setting parameters, moving, and so on. Down the road, I think, where we might want to end up is something like a PostScript of chronochromic algorithms. PostScript is a page description language that sort of allows you to describe anything you might want to put on a page, PDF now, portable document format. I think ultimately running a program on every image that turns it into different colors over time is the way this will end up going. But we're just sort of evolving in that direction with all these dials and sliders and things. By the way, well, I'll show you in a minute. So anything else people want to see in the demo before I go back to my slides? Questions about the demo? Okay. All right. So I'll tell you briefly what we have today. I already showed you the Colorfy web player that Shun's been working very hard on. There'll be a URL at the end if you want to try it. And the tuner that'll be coming soon after that. And I guess I showed you the builder, which is also going to come out soon. We've also been playing with things like, I have a MIDI controller here that I hook up to my tablet. And my wife and I took a fall colors tour a couple of weeks ago. Driving around, I had this propped up on the dashboard, and I was using this to control the sliders. So that I was developing algorithms in real time. And I think that when we get to the stage where people are walking around wearing goggles or smart glasses and seeing the whole world this way, they may well want a smaller version of this to like tune things up as they go along. And you may too when what you're looking at is infrared. And then as of last week, Shun got a basic algorithm of this working on the MetaQuest. So we're getting there to the point where you'll be able to just walk around and see more colors if you're colorblind. So how's this going to help? Some of it's pretty obvious. Vocationally, it'll let people be pilots, truckers, let them be visual artists with more confidence. I never went into the arts because I always thought I'd make a fool of myself. In retrospect, I kind of regret that because I know there are colorblind artists who've done interesting things. But I just sort of assumed it was a door that was closed to me. But as I said, I can get near perfect scores on colorblindness tests. This will help the colorblind in the form of native phone apps, browser plugins, desktop accessories for operating systems and TVs and phones and things, binocular headsets, as we just showed. Scientific instruments, if you're a radio astronomer, this is going to be real useful. Rifle scopes, basically anything with a digital screen. I think it makes sense to think about building this into eventually. Yeah. But beyond colorblindness, oh, yes?
Color-sighted people see color blindness better?
Well, that's actually, that's a settled problem. There are sites on the web that will allow you to take any picture and show what the different types of colorblindness see. I don't think they work for protanopia because the input and the output look exactly the same. That's a joke, yeah. So lights are a fine question, and you should chime in with your experience. I find that traffic lights are designed so that colorblind people can generally identify them by position. But green lights look just like white lights to me. Red and yellow lights look pretty similar, especially at night. Ed was just telling me he got out of a ticket for running a blinking yellow blinking red because he thought it was blinking yellow. So,
and sensors, or does it have to be a screen?
well, I think this will work embedded in smart dashboards on cars, or driving. You could conceivably have goggles, or you could have a dashboard display that you glance down at to see the colors in the scene ahead of you. There's a number of form factors. I don't advocate like being a pilot and holding up this tablet the whole time and trying to fly the plane, right? But yeah.
For you, or is it?
I've never found it useful at all. You know, there are tools that I can use to point at something and say, oh, that's red. Okay.
I'm curious because these things are, like when I teach interaction design and say, hey, Apple got it, and they have these tools, but I'm actually never sure it's actually sufficient. So it's good to hear.
Yeah, I think, you know, I think one of the reasons there aren't like serious communities of the colorblind or foundations for the colorblind is that there's almost nothing for them anyway. You know, so I'm hoping that'll start to change with tools like this. But beyond colorblindness, as I said towards the beginning, the approach we've taken here is one of mapping invisible data onto the visible screen, along with what you normally see visibly, using changes in color over time. And you can use that, first of all, for multispectral stuff. We can use it to give you infrared or ultraviolet, or to be able to walk into a room and say, oh, the Wi-Fi signal is best over there. You know, there's a lot of scenarios you can imagine if you can see other spectra. But beyond that, it can also be used, well, I guess I'm about to say this, so I should go through my slides. On the multispectral, one thing worth mentioning is radio astronomy. We're all used to seeing these radio astronomy pictures with simulated colors, right? Which I can then look a little better for me. But the fact is, if you take the original radio astronomy data and go directly to this kind of algorithm, you'll be able to see the red, blues, and greens, and the ultraviolets, and the X-ray images, and so on. You'll be able to layer over it as algorithm. So it'll be a kind of visualization that'll allow normally sighted people to see more at once. And there are lots of other little uses for it. Flowers are just gorgeous in ultraviolet. I would love to walk around and see them. If you're worried about your kid missing a spot putting on sunscreen, it would be really nice to have ultraviolet, because you can just look and say you missed a spot. You know, it's because it's black in ultraviolet. And one of the first things we're probably going to do this on is there's starting to be IR add-ons for smartphones. And so we're probably going to be able to use these algorithms there. But it's also going to be useful for visualization of non-visual scalar information, by which I mean anything that can be computed about a scene and mapped onto 0 to 255, like a color axis. So you can imagine an AI attached to a soldier's headset, analyzing a scene for the most dangerous spots and basically creating a color of danger. And the more danger color there was over there, the more you should pay attention to that spot. Might be useful to a policeman on the beat too. Anything that you can apply, as you know, that you can transform into information relative to spots on an image, we could animate that way. I also think there's potential for new tools for artists and for people making music videos, because these algorithms naturally fall into rhythms that could match up with music. So I think there's some cool art potential here. And also, I think AR, you know, lots of AR techniques are already out there. I think being able to add these synthetic colors in AR, I don't know if that's the right term for them, would make it easier to stitch together real and virtual reality, because you sort of have more options for how to represent things. And then the most exciting and promising thing, this summer I was giving a demo of this to a small group of people, one of whom had very, very low vision. She had glaucoma and cataracts and something else. And she went, "Oh, I can see this much better now." And we were like, "Why?" So I've since tried it on, I think, 5 people with low vision. 2 were like her, said this makes it a lot better. 1 said it made it a little better. 2 said it didn't make it better at all. So that's the full set of anecdotes I have on this. But I think there's potential here to help some low vision people. And I would love to have people who wanted to research that. So everything on this slide is a potential thesis topic, if you're looking for thesis topics. All right, and I really think we're just at the beginning of a really interesting journey here. What you see in the upper left of the screen is called the Nimrod lens. You can find it in the British Museum. It's the first known magnifying glass. At some point, after people figured out how to make glass out of sand and fire, somebody picked one up a piece and said, "Oh, this makes things a little bigger." And then sometime after that, they had gotten it this far refined. And after 3,000 years, you go to the eye doctor and they click all these things. Well, they do better than that now. But the point is, that was a long road. And we're at the Nimrod lens stage of this. There are sextillions of decillions of algorithms with our current prototype alone. And I've tried several dozen of them. You know, there's just a whole lot to be experimented with here. So yeah, we're on this end of the journey if you're looking for a thesis talk. So opportunities to help play with us, research. First of all, we need testers and experimenters. You're welcome to join us. Good. But tell your colorblind friends. I'm particularly interested in finding colorblind people who are, well, I'm most interested in letting colorblind kids play with it, frankly. But I'm particularly interested in finding colorblind people who are technical enough to start building and playing with algorithms and helping us find better ones. So I already talked about all this. There's lots of areas to research into what the best algorithms are, all thesis topics. We're also hoping to grow a community of developers for the colorblind, developing these algorithms. We're trying to set up, we're first of all, the company's promising no patent assertion against non-commercial use for the colorblind. But we're also trying to incentivize innovation within that community so that people who come up with cool inventions or technologies within this framework, we're going to have a pool of equity so that we can share some of that with them. So we're trying to keep the community and the company intertwined somewhat. I don't know if that'll work out. We're trying to do the right thing. But let us know if you want to play. And you can go to colorfy.com to play with it, or you can scan this URL, or you can send me email. And that's it. Thank you for your time. And I guess we have time if there's any questions.
I think it was 30 frames per second video. If you were showing those, colors at 30 seconds, 30 frames per second faster, do you still see it pixelated? Like, don't consciously realize.
There's a speed at which it becomes a blur, right? And if you ask me what the best speed is, I have no freaking idea. Okay, I've been playing with this stuff for almost a decade, and I can tell you what makes me happiest looking at it with it, right? And I've done a few dozen subjects a few years back, but even I am not consistent. There's sometimes like, there are some really pretty still scenes that I actually like to linger on and have I can show you an example because it's kind of neat to watch. Let me call up this demo. There it is. All right. And I'm going to get out of your way, and I'm going to make the cycle time much longer. Oh, this is the wrong algorithm to use for it. I'm sorry, just a second. So the hue rotation is going much slower now. Actually, I haven't slowed down the saturation rotation, but I should go to something that's just hue rotation. Just a second. All right, I'm messing up the demo because I'm trying to do it in real time. But the point is, if you really slow down the cycle, it's sometimes just really beautiful. when you're seeing new things that you don't see before, because some of the differences just sort of fly by. Other questions?
Back to what you said initially about military use. One of the things I've stayed away from being a research in AR. I can see there's significant potential here for soldiers to see things that they would otherwise not be able to see. So you're not addressing the machine to use you. It's going towards the superhuman, like the picture you put in your talk. So how do you think about this not becoming a weapon? And how much do you actually think about it? I mean,
I think about it a lot.
It takes somebody like you to be invested in guiding some of this research. So my stance in the past was like to stay away from it, but I'm now feeling more like one should be more involved to help.
Yeah, I had a student back when I was at Carnegie Mellon. One of my students was in ROTC, and he was a pacifist. And at one point I asked him, how does this mesh up? And he said, do you want people who don't feel the way I do making these decisions? And I've always been conflicted about this, but when I went to grad school, I realized my whole grad school was being funded by the military. And that's just the way advanced research is usually funded in this country, at least. And so I try to do more good than harm. Like I said about my view on the internet, right? Is that I hope that this technology will do more good than harm. In the case of the soldiers, I'd rather think of a color for safety for them fleeing than a color for targets. But technology tends to be very morally neutral. I was driven to do this because I wanted colorblind children to see more colors. I don't see any way you could put this technology into the world and not have it applied to the military. And frankly, making it even more complicated is they're the ones who are most likely to throw money at advanced development on something like this. So I regard it as a sort of a very deep and impossible dilemma for someone who wants to be doing advanced research and who doesn't want to be promoting war. I don't know. I know you've worried about these problems for a long time, as I have. I suspect that my 22-year-old self would view me as something of a cop-out by now. I'd prefer not to, yeah, I don't know. I don't know if my daughter views me as a cop-out. Yes.
So talk about how if someone's using this, let's say follow or something, how it could be distracting or annoying to have these sort of all these movement and stuff, and how that kind of outweighs the benefits outweigh the potential damage.
So I can tell you, yes, it is distracting. And the more things that are changing, the worse it is. So in this image here, there's a fair amount changing. It's still being limited by what's reddest. The red threshold is fairly low right now. A lot of that's going to be a matter of taste. Just like there are some people who can't take any flashing images. Did Colleen leave? Are you still here, Colleen? She left. Yeah, I hope it wasn't because of the flashing images. People are different places on that spectrum. What I find, and what most of the colorblind people who tried it find, is that the extra things you see make up for it, and you can start to get used to it. Now, we have never yet had this in a form where you could just walk around all day wearing it. My guess is you'll get more used to it rather than more annoyed by it, but I don't really know. Charles.
Curious about this presentation as a data density issue, because when you are looking at something, let's say, for example, you are XGB, I am RGB, 24-bit, 30 frames per second. But if you're going multispectral, you are compressing that data into less space. How are you addressing just the fidelity and then the ability for the brain to discern? Because if you take the Fully-M spectrum and shove it into, let's say RGB, or for you, something else, does motion alone make up for that? Or
I doubt that you can take the full spectrum and ever see it all at once. I do doubt that. And I'm sure that no matter how many algorithms we build, you'll be able to see more of it than I will, because you have an extra axis of native color, right? So the limit is undoubtedly higher for you than it is for me. And there is a limit, there's no doubt, but you can see more. That's the basic message here. I'm pretty sure you could put on a headset that gave you both ultraviolet and infrared, which are being the two nearest tend to seem like the most useful. I think there's enough room to represent that because, well, the brain is an amazing flexible instrument, right? And it responds to changes and differences, and differences in both color and time may well feed into some of the same neural mechanisms. I mean, that's what it feels like to me.
Like one clarifying question. So would it be fair to say this is like an attention algorithm that's just telling me like where to look if I can't see things?
That's a good way to put it. So this is, again, almost a philosophical question. You might say that in the eyeball, the answer is no, and in the back of the brain, the answer is yes. Because by the time you've gotten to the concept of red, you may have gotten it in there. But you're absolutely right to say it's about attention. Because when I see this picture without Colorfy right now, it's not like I can't see all the flowers. It's just they blend together because they're all the same color or close colors. Just this morning, or last night, I was watching my grandchildren take a bath, and there's a bath mat that had a bunch of colored flowers on it. And I happened to take out Colorfly, and I noticed that each of the flowers had another colored dot in the center that I didn't even notice, right? Now, when I stopped using Colorfly and looked carefully, oh yeah, it's a slightly different color, right? So it is about attention. The fact that it was flashing drew my attention to differences that were not big enough for me to notice before. But it's also the case, I think, for most colorblind people, that if they try really hard, they can see, a little more red. It's a matter of effort.
Back to the banana example, could you use it to see that food is going rotten, like past normal human vision? Do you think that's
an interesting question. I don't know, for example, what rotten meat looks like in ultraviolet or infrared, right? It's quite possible that it's plain as can be. It's like, I think I mentioned sunscreen. You put on sunscreen and it's completely clear, you see nothing. In ultraviolet, it blocks everything, your skin is black, okay? So, some things just become extremely obvious. And one of the weird things about now finally having this and being able to walk around places and see more colors is I never know where to look. Say, was that interesting? Oh, no, that's not interesting. And my wife will often tell me, you should look at that. You should look at that with colors. So we're all in that boat with regard to what would ultraviolet or infrared help with. We know a few things, right? Because infrared cameras have some commercial value. By the way, it's worth comparing this to conventional infrared imaging techniques. When you use an infrared camera today, it shows you an infrared image as green or something, right? And you lose all the natural colors. And that's very useful for some tasks, but better for everyday use and probably better aesthetically would be if you saw both at once, which is what these algorithms let you do. Any other questions? Well, do tell colorblind people that that we're open to testers. And I'll put that slide back up, and thank you for your time.